So this video is on simulating what microscopically happens in a donor-acceptor domain. So this is a very idealised view of a donor-acceptor domain, but it's a nice way to look at this problem. So what we've got a ball here in the simulation. Oh, and before I go further, just let you know that you can get this from Exciton domain simulation in the new simulation window. So we've got a ball that represents the donor material, and we've got a box in which this ball sits, which represents the acceptor material. So we've got effectively a box and a ball. The ball is donor, and the acceptor is everything that's not in the ball. And we've got light coming in the top, and we're going to have photon generation or exciton generation within the ball. And what we're going to be doing is we're going to be solving the exciton diffusion and dissociation equation. So this one here in the manual. So this is the GPDN manual that you can download. And we're going to be looking at how effectively these parameters here affect exciton splitting. Now, if you think about this problem, you've got this sphere, and if you generate an exciton in that sphere, then it's got to make its way to the edge of this sphere, to the interface between two materials before it can dissociate. But if you've got radiative recombination going on within the sphere, your excitons are going to be annihilated before they get to the edge. So you can play games like, okay, what happens if the sphere is very, very small? What will the exciton dissociation rate be? What will the loss be? If the sphere gets bigger, what happens? Is there a perfect size? So you can sort of effectively investigate how all these parameters affect the overall exciton splitting efficiency. So that's what we're going to be looking at. Now, in the past, it's been very difficult to do these type of simulations because we didn't have all these parameters that we need. Like, we didn't really know the diffusion length, we didn't know the exciton lifetime and things like that. However, it's becoming increasingly more common to measure these parameters, and this whole simulation was spurred on by this paper that I was involved with that's going to be out. So today's the 2nd of May, this is going to be out I think next week, so I'll release the video after then. And it's called Single Junction Organic Solar Cells with over 19% efficiency enabled by refined double fibril network morphology, and this will be in Nature Materials. And these people in this paper did a very nice job of having a few materials, and they measured these parameters effectively for this equation, for these materials. So these are now knowns. So I'm just going to explore this type of simulation in this video. So let's just run the simulation and just see what happens. So there we go, we've run it. So let's look at the output. So first off, let's look at the photon generation within our sphere, because that's quite easy. So let's look at that. So what we're going to be doing is we're going to be taking, so here's the axis. We've got X, Z, so and there's Y going the other way. We're going to be taking X, Z slices through this ball. So we're going to be sort of going balls, showing the inside of it now. But let's put that back on, just so we can. There we go. So we're going to be taking X, Z slices going up through the ball. So let's run this, and we can basically see at the bottom of the ball. So right down here, we've got some photon generation in the middle, and then as we go up through the simulation, the photon generation, so up through here, the photon generation effectively follows the profile of the ball, as you'd expect. Good, okay. So now let's look at the exciton density within the device. So we're going to be within the ball. So this is we're looking at X here. So here's exciton. So now this follows this typical exciton, typical diffusion profile. So at the edge of the ball, you're going to have 0 excitons, and you're going to have some maximum excitons in the centre of the ball. So we're again scanning through the ball. So we're going up through here, looking at exciton density in the ball. So let's just make this a bit more colourful, and we can examine what's happening to the excitons of the ball. Let's plot this in 3D now. So just needs a bit of a kick to make it show. So move this around. Unfortunately, my monitor's a bit small. So let's let's take a cut through of this ball so we can see what's going on inside. Cut through X, there we go. So now we look in, and we're actually plotting the exciton density within this domain as a function of position. So we're sort of scanning through, taking snapshots throughout the simulation. And let's now look in the other axis. So rather than just the X, Z axis, let's look in the Z, Y axis. So we can now scan through and really see what the exciton density is doing in the device. And that's all very good. We can see this simulation is vaguely sensible, and we can sort of say, okay, well, let's now do some maths with this. Okay, so let's get rid of that. So if you look, I'll just put this away. If you look in the output directory, there's a file here. It's a bit hidden, but it's called excitonsiminfo.dat. Now, if you double click on that in G3M, you won't see anything. But if you open the text editor, like I've done here, you'll get something looking a bit like this. And what we've got here is we've got this is effectively a breakdown of what's happening in our simulation. So we've got the layer 0, and its name is layer. So it's just that's this whole box here. And in there we've got shape 0, which is its name is called shape, which is the ball. Okay, so we've got the layer and the ball. And each one of these terms represents the spatially integrated value of whatever process we're looking at. So here we've got total generation in the layer, and here we've got total generation in the ball. So in the ball, we've got lots of generation, and we've got 2 to the 5 worth of generation. It's normalised by volume, so it's it's normalised by volume. So you're meant to look at the ratios, these numbers, rather than sort of the absolute values. I can dig out the units as needed if somebody needs that. So looking at generation, we've got lots of generation going on the ball because that's the donor, obviously, and there's hardly any generation in the acceptor, so it's 2 orders of magnitude lower, and that's probably sort of a bit of numerical, noise or something. So effectively that's 0, and that's very big. Now this is the KAR, so the radiative decay rate. So this is I think it's KPL. I think it's that one there. KPL. And we're getting effectively a lot of exciton self-annihilation within this ball because we've set that parameter to be high. And then at the edge of this, so the interface between the ball and the acceptor domain, we've got very high dissociation rates. We've got a very high dissociation rate of excitons at that interface. So you can see we've got no dissociation within the ball, dissociation on the interface. So what we can do is we can compare the ratio of the dissociation rate at the interface to the generation rate. So we divide this divide this by this, and that effectively is the dissociation efficiency. And in this case it's 89%, and that's that number divided by that number. Now, if, for example, if we increase a loss mechanism, so the radiative exciton annihilation within the ball, so we're increasing, let's increase KPL, so let's go and do that, look at the electrical parameters, and find the sphere and increase KPL by, let's just pop it up by an order of magnitude. Now, incidentally, there are some electrical parameters being shown in the electrical parameter editor, but these aren't actually being used in this simulation because we've selected selected exciton simulation type, so this turned off all the actual proper electrical drift fusion simulation. So we're only concerned with this bottom panel here. So I've just boosted the radiative decay rate of excitons within the sphere by an order of magnitude. So let's just go ahead and rerun that. Chug, done. So now reload this. So this was say 89% efficiency, increased the radiative rate, which is this one. So let's just look at that. So this has gone up by an order of magnitude, and this has gone down by 50% or whatever. So we can sort of play those types of games and sort of ask questions like, well, what happens if we make the sphere smaller? So I'll try to do this now. So let's make the sphere a bit smaller. So let's make this 4 for looks like something off Star Wars actually, doesn't it? Let's put, whoops, put this back in the centre. There we go. So it will change the size of it. We can rerun it, and as you'd expect, all these numbers will change. You can play all sorts of games with that, play with the numbers, play with the sizes, things like that. So I hope you find that useful. So effectively, this is a tool for telling you what your dissociation rate will be if you know all your parameters about your device, about your material, sorry. So there'll be a bit more of a manual. I'll write some stuff in the manual probably when I get round to it. There is some stuff in here describing a few bits about the equations it does, but I'll fill out these sections when I get a moment. So hope you enjoyed that. Thank you very much, and yeah, goodbye. Thank you.